All right. Given that this is a meeting that's meant to be kicking off these activities, I thought I wouldn't give a talk on the sort of latest thing that I'm working on, and instead I would just take a step back to try to put at least part of the kinds of questions that are going to be some of the questions that are going to be explored in this collaboration in a wider context. Just speaking for myself, I've been working on sort of related questions for around 15 years now. And the past 15 years have seen lots of interesting developments that have, I think, brought us to a point where the next 5 years promise to have a lot of interesting things happen, a lot of exciting things possibly happen. That's part of the raison d'etre of this collaboration. So that's what I'd like to tell you something about, is the sort of wider context of what has brought us here. And to give you some concrete examples, so it's not just a lot of blah, 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 but just some concrete examples of what these ideas look like, just so most of the people who aren't experts have some picture for what potentially what great things could come out of this endeavor. The experts have heard me drone on and on about things like this for a long time, so if they want to go to sleep, that's perfectly okay. Although I hope it's at least interesting to try to put this the broad story together in a coherent way. So I'm going to be talking about this sort of intersection between particle physics, cosmology, and mathematics that I think broadly fits under this title. At least the way I think about it is fundamental physics and some interesting new structures in mathematics that are loosely associated with this phrase positive geometries that live at infinity. And it'll be clear what I mean by live at infinity as we proceed. To begin with, let's just remind ourselves what the big revolutions of the last century were about in fundamental physics. I think obviously the two big revolutionary developments were the unification of space and time into space-time by Einstein, and sort of 10 times more amazing revolutionary discoveries of quantum mechanics. And the two of these structures together, space-time and quantum mechanics, Lorentz invariance and unitarity, if you like, putting these two big principles together, it turns out to be tremendously constraining on what possible laws of nature can look like. And the kind of theoretical rubric that lets us speak of laws of nature, potential laws of nature that are that have both of these principles operating simultaneously was started to be slowly developed in the 1930s and is known as quantum field theory. I think it's fair to say that to this day, we don't really understand deeply what quantum field theory is really about, but we understand a lot about it. And we also understand a particular instantiation of quantum field theory, the so-called standard model of particle physics as well as cosmology, that describes everything that we understand in fundamental physics over the entire sweep of distances, from the smallest distances we've probed at accelerators like the Large Hadron Collider, 10 to the minus 17 centimeters, 1,000 times smaller than the nucleus of the atom, all the way out to the size of the observable universe, around 10 to the 10 light years, 10 to the 27 centimeters, associated with the scales of cosmology. So it's amazing that there's one uniform set of theoretical ideas that holds sway over this entire range of distances. And this is what makes it much more stark and surprising what the storm clouds are that we've understood for many decades now are confronting us as we try to move beyond our current understanding. Because the storm clouds are not about this or that detail. They're not about this or that observation that doesn't quite fit, or this or that particle that may or may not be discovered at a collider or something like that. The storm clouds are much more structural. They're much more fundamental. They go right to the heart of these two grand principles that are so tremendously constraining and guiding to what laws of nature can look like. and maybe the sort of most the one that's most universally agreed upon by theorists, is that as a consequence of the presence of both gravity and quantum mechanics, the notion of space-time, one of the pillars of our understanding, is very likely approximate. The notion of space-time is unlikely to be a fundamental one. It's unlikely to survive as one of the axiomatic ingredients of whatever our next understanding of physics is. And this is a consequence of some very simple thought experiments. So if you take my terrible picture of a magnifying glass here and you look at a smaller region of space, because of the uncertainty principle, you have to use higher and higher energies to probe shorter and shorter distances. And in a world without gravity, there's nothing wrong. You just ask for more energy and you probe shorter distances. But in a world with gravity, eventually something very bad happens. You put so much energy into such a tiny region of space that you collapse the region that you're looking at into a black hole. And that stymies your efforts for seeing what's going on in there. This means that there's no operational way to give meaning to distances in time that are small enough where this phenomenon happens. And of course, this happens at the famous Planck length in Planck time, around 10 to the minus 33 centimeters, 10 to the minus 43 seconds. At these scales, our notion of what space and time are simply break down. Of course, you could say this thought experiment means that space and time exist, but there's no way to operationally measure them. That's, of course, your prerogative to believe such a thing. But over and over again in the history of physics, we've learned that when we have these thought experiments that tell us that some notion can't even in principle be given operational meaning, it's likely that that notion is approximate. It's not really there in the next set of laws. In this case, it's very startling that the thing which is not there is a notion of space and time itself. So these things are relevant, for example, near the Big Bang. When we run the picture of the expanding universe back in time, what's happening near the Big Bang singularity is simply the notion of time is breaking down, amongst many, many other things. There's another aspect of this which is worth emphasizing. It's really the same thing, but the idea that the goal of fundamental physics is essentially reductionistic. So the laws of nature are given to us at incredibly tiny distances, and we get there by going to higher energies. And so higher energies as tinier distances is where all the action is. That's the basic reductionist paradigm. That's fundamentally wrong when you have quantum mechanics and gravity. It's exactly the same thought experiment, just continued. So imagine you collide particles against each other. Well, the energies get much larger than the Planck energy. Then you start making black holes that stymie you seeing what's going on in there. And if you get frustrated and build an even higher energy accelerator, what happens? You make an even larger black hole. So the idea that higher energies at shorter distances turns on its head, and higher energy starts turning into longer distances again. So once again, the idea that all we need is arbitrarily high energy accelerators to probe arbitrarily short distances, and that's where the fundamental laws are given, is essentially wrong. So the reductionist paradigm itself is essentially wrong for this reason. So that's a kind of a quite startling set of issues about the sense in which the notion of space-time is breaking down, which normally people talk about in talks like this. But that might give you the impression that the issue is only localized at very short distances near the Planck length. That's the only place where any of this stuff matters. And in fact, it's much more interesting than that. It's much deeper than that and somewhat more subtle than that. There's a precise sense in which the notion of what sort of space and time are is sort of breaking down everywhere, not just, I mean, in a precise sense, of breaking down everywhere, not just at very short distances. And this has to do with a very important fact about what it means to know something in quantum mechanics, what it means to observe something, what it means to measure something in quantum mechanics. Quantum mechanics needs you to do two things to make precise statements about the world. First, it's a probabilistic theory. So you have to, in principle, do experiments over and over and over again, infinitely often, in the limit infinitely often, in order to extract precise results as probabilities. So that we talk about in textbooks all the time. What we talk about less in textbooks is that we have to do the experiments with infinitely large measuring apparatuses. And there's many reasons for that, but one of them is that if the measuring apparatus itself is finite, then the measuring apparatus itself has quantum mechanical fluctuations, and we can't be precise of the outcomes of the measurements that it's recorded. One reason we don't talk about this second thing, effect, as much as the first one with repeating experiments is it's practically much less important. If you do an experiment n times, there's a statistical error of order 1 over square root of n that really matters, and experimentalists report it. This error that we're talking about says that if you do a measurement with the measuring devices has sort of n degrees of freedom, there's an intrinsic systematic error of order e to the minus n associated with it. So that's practically really minuscule, but conceptually it's very important. It means that there's no arbitrarily precise measurement that any finite measuring device can make. And that, in turn, means that there's no precise meaning to any measurement you can make in a fixed size room. So the fancy name for these things are local observables, but it's literally any kind of measurement you can make in a fixed region in space and time. And the reason is that if you're going to make the measurement, you want to make it arbitrarily precise, you have to make the measuring apparatus bigger and bigger. That inevitably makes it heavier and heavier. And before it gets infinitely big to make the measurement infinitely accurate, it gets so big that it collapses the whole room into a black hole. And then, of course, you all get crushed in the singularity of the black hole, and that stops you from doing the experiment infinitely often as well. So in any fixed size room, there's a systematic limit to how accurately you can talk about anything. And once again, it's the same sort of philosophy. Every time it's happened to us in physics before, that there are systematic obstructions to certain observables. The quantities that we're trying to observe do not actually make sense. They're not part of the real physical theory. And in this case, it's, again, even more startling that it's any kind of local observable does not make sense. So what does make sense? The only kind of observables that make sense are experiments where you can make your measuring apparatuses bigger and bigger, but push them further and further apart from each other out to infinity. So for example, you can have apparatuses spit out particles from infinity. They can crash into each other and go back out to infinity where they're measured by infinitely big apparatuses. Those are legitimate observables. They can be measured in principle with arbitrary accuracy. Those observables are fortunately what we like talking about in particle physics all the time. They're very, very close to what we do at accelerators. And we'll talk about them a lot, of course, in the rest of this talk. They're scattering processes, and the observables are associated with scattering amplitudes. Okay, but those are not only practically important and the bread and butter of particle physics, but they're also conceptually important as being the only kind of observables that make sense, at least if your space-time has these asymptotic regions that goes out to flat space where you can push things out to infinity and to both produce and detect the particles before and after the collision. Famously, around 30 years ago, string theorists discovered a cousin of these kind of observables and a cousin of our kind of space-time. In the world inside a tin can of anti-de Sitter space. So this is the closest we can come in physics to putting the universe in a box. It's really like the geometry is really like a tin can, but there's the geometry in the interior is warped in such a way that while the distance from a point in the interior to a point on the walls of this tin can is infinite, light takes a finite amount of time to sort of bounce off the wall. So that's a sense in which it's really like the world in a box. But in this world, you could run the same philosophy. You can say, what are the, in principle, observables I can talk about? And here it would be pinging the sides of the box and sending waves into the interior that crash into each other and come back out to the walls of the box. But the observations start and end on the walls of the box. Just like for scattering processes, the observations start and end at infinity. The interior of the space and time is not part of the observation. It's part of what's in your mind as a theoretical physicist for trying to explain the observation, but it's not part of the observation itself. And in this context of the universe in a tin can of anti-de Sitter space, you can really push this philosophy to the logical conclusion and say that if the observation starts and ends on the walls of the tin can, then maybe I never need to talk about the interior of the tin can. Maybe there's a theory that only lives on the walls of the tin can that lets me correctly predict the outcome of all possible experiments that I can think of where I ping the sides of the tin can. This is the idea of holography. It's been studied actively for 30 years. It'll be studied actively for many decades more. A lot more is understood about it, of course, than it was 30 years ago. It gives us our first example of how sort of space can emerge out of no space. space and gravity and strings and all kinds of other things can just emerge from the strongly interacting dynamics of a completely ordinary quantum mechanical system that lives on the walls of the box. But crucially here, the time that flows on the walls of the box is exactly the same as the time that flows in the interior of the box. So this is not yet an example of emergent space-time. It's just emergent space coming out of quantum mechanics in some interesting way. So that's the one set of questions is about the doom of space-time and what might replace it and what some of the ideas are that have already been explored for taking us in this direction. If I jump to the opposite end for the hardest problem, the most difficult problem, the one that we have, I think, no clue yet how to think about properly, this comes to us courtesy of cosmology and the discovery of the accelerating universe in the late 1990s. And the accelerating universe opens up a huge number of Pandora's boxes in thinking about fundamental physics, almost all of which go back to this essential thing of what quantum mechanics needs. Quantum mechanics needs this division of the world into two parts, an infinite part, that's the sort of measuring apparatus that's looking at a finite system. But you need this funny division of the world into the infinite thing that does the looking and the finite thing that's being looked at. That already is sort of, gravity doesn't like that. As we just talked about, gravity, everything gravitates. Gravity is universal, so it does not like this artificial division of the world into pieces. But at least in universes that look like flat space at infinity, or they look like anti-de Sitter space at infinity, you're still left with something you can talk about. The difficulty in our accelerating universe is that there's nothing left we can talk about. And that's because in the accelerating universe, we're also surrounded by a finite size horizon. Light from things that are further than that are cosmological horizon away from us will simply never make it to us because the universe is doubling in size as a constant rate, and so the light will just never make it to us. So what we see out there in the universe now is what we're ever going to see. We're not going to see any more. And that means that there's a fundamental finiteness that's thrust on us by cosmology. And that finite, it's enormous. The universe is enormous, but it's finite. And the finiteness means that every single possible quantum mechanical question does not have a precise answer. Okay, there's nothing that we can speak of with perfect precision. So not only the issues of cosmology force us to think about the emergence of time as well as of space. That's kind of obvious, maybe even obviously at the Big Bang. But maybe even more startlingly, it forces us to begin to think about extensions of quantum mechanics. I want to say that this is not universally agreed upon. It's certainly my own interpretation of what's being called for. I want to stress that I'm not some crackpot who's saying that quantum mechanics is wrong when a random experiment is done in a grad student office somewhere. I believe every time quantum mechanics is able to give a precise answer to a question, it will give the correct answer to that question. But there are situations when we try to apply quantum mechanics to the entire universe and accelerate, especially to accelerating universes, where quantum mechanics is unable to produce an answer to a question. And those are the situations where we start needing to think about what might go beyond it. All right, so these are our two sort of huge questions of what might replace space-time, what might extend quantum mechanics in some sense. I've spent around 15 minutes now talking very abstractly about these highfalutin questions. But I want to now switch to a second set of questions that are much, much closer to home, which, as you'll see, resonate with this first set of questions in what has always struck me in a quite dramatic way. Let me just back up and say that you might realize that all of these are sort of big conceptual problems, and you then might think, well, what am I going to do about them? So I can say they're wonderful problems, but I'm not going to gape at the sky all day and just say how great the problems are. You have to know what you're doing when you wake up in the morning, right? You have to be able to work on these problems in some way. And maybe the most obvious way to work on these problems is to think about the places where they matter at order 100%. So the most obvious way to work on them is to imagine what happens if you throw yourself into a black hole, or what's happening at the Big Bang singularity, or how to make sense of de Sitter space. Those are the kind of theoretical questions that at least these issues hit you at order one. It's also fair to say that these are questions with extremely limited guidance from experiment. Um, and this means that you're almost entirely, stewing in your own juices as a theorist if you want to work on them. There's another sort of strategy that you can take though, and this is a strategy that some friends and I have been pursuing for, as I said, around 15 years. It's just another strategy, which takes the following sort of inspiration that if something like this is true, if we have to replace space-time with something else, if we have to extend quantum mechanics, these are such humongous deals that it's very unlikely that they're going to leave all the rest of the way we think about all the rest of physics totally untouched. And of course, there's precedent for this. We've had similarly big revolutions before. When we went from classical to quantum, for example, we had to lose the notion of determinism. And that seems completely insane. If you're a Newtonian classical physicist, how could you possibly lose determinism, which is the most important feature of Newtonian mechanics? If someone came and told you in 1850 that in 1930 you're going to lose the notion of determinism, you would think they're totally insane. But if you believe them, then you would have to wonder, how could it possibly be true that the thing that's the most important feature of the Newtonian worldview turns out to go away? How can that be true and still have the Newtonian picture be so accurate? And it could inspire you to say that, well, that since determinism is gone, there must be some different way of thinking about Newtonian mechanics where determinism is not the most important idea. It somehow comes out derivatively in some secondary way, but is not the primary idea. Why? Because determinism really isn't there. And so the real theory doesn't have it. And so the way the real theory reduces to Newtonian mechanics can't have it either. It's not something you can gradually turn on and off. Is there such a way of thinking about Newtonian physics? There is, of course, famously. It's the principle of least action is the way we have of thinking about Newtonian physics in this way. And there it looks like the particle travels from A to B, taking every possible path, smelling out every possible way that it can take from A to B. It doesn't look like it's deterministic. It turns out that the equations are the same as F equals ma when you do the variations in the allowed ways. But the principle of least action is the sort of stepping stone to quantum mechanics. The principle of least action can be naturally deformed to the path integral picture, but not Newton's laws. Okay? So that's a remarkable feature of the laws of physics at any given time that can be formulated in radically different ways from radically different starting points. And some of them could be better suited to the jump to the next level of description than others. So that's the inspiration that we're going to take here. Now it's going to be, we've got to get rid of space-time, we have to extend quantum mechanics. So what we're going to try to do is learn to talk about ordinary physics, completely ordinary physics, not speculative things about black holes and the beginning of the universe and all that stuff, ordinary physics, but somehow tying our hands behind our back and refusing to use space-time and quantum mechanics in the standard way in order to get the results. Okay, so that's the thought. But as you'll see, and this is what the sort of wonderful, delightful surprises of the correlation between this highfalutin abstract mumbo jumbo and practicalities is that, in fact, it does not end up being tying our hands behind our back at all, because there's a second clue lying right underneath our noses that there's something very, very wrong with the standard space-time way of space-time quantum mechanical way of thinking about these things, which is what happens when you actually try to calculate fairly normal physical observables that are happening for processes that are happening all the time in nature, including, of course, in man-made things, human-made things like accelerators, like the Large Hadron Collider. And these are scattering processes, scattering amplitudes. So that's the obligatory picture of the LHC, 27 kilometers around. We collide protons at 0.9999999 times the speed of light. And the quarks and gluons inside the proton have sort of head-on collisions, and we want to figure out what the rates are for the head-on collisions between the quarks and gluons in these very, very high energy colliders. Now, this is not, on the face of it, an exciting place to look for new ways of thinking about physics, because everything about this has been understood in principle since the 1940s or 50s or 60s, really going back to Feynman, right? So Feynman taught us a way of thinking about, famously in terms of the Feynman diagrams, but also a way of thinking about quantum mechanics that made Lorentz invariance and the rules of quantum mechanics as manifest as possible at the same time in the sum over histories picture. So Feynman says that the amplitude for a process is the sum over all the histories of an e to the I action. And the sum is about quantum mechanics. The sum is about summing all the possible ways that things can happen. So that's about quantum mechanics. And it's a sum over space-time histories, and the action is a local action. So this is what's the fact that we have a space-time and local interactions in space-time. So this formula has locality and unitarity are sort of part of the are built in. Now that's fine, but if you try to get the answer to the question of 2 gluons and the proton come in and 4 gluons go out, you already have an explosion of complexity, just combinatorial complexity in drawing the pictures and following the textbook Feynman rules. And depending on how big you write and how you go about doing the calculation, the answer might be 100 pages of algebra, a few hundred pages of algebra. 2 to 2 is something you put on a problem set. 2 to 3, you would not torture anyone with on a problem set. 2 to 4, you definitely would not torture anyone with on a problem set. And well, ahead of time, there's no reason to think that these questions have simple answers. It looks complicated. In fact, it looks just like not every question has a simple answer. This looks like a classic example of a complicated question that's going to have a complicated answer. And part of the prejudice of fundamental physics is that we only care about questions that have simple answers, and everything else is some kind of engineering. So this looks like some kind of engineering, and oh well, someone has to do it because the experimentalists need to know the answer for 2 to 4, 2 to 5, 2 to 6, 2 to 7 even. So someone has got to do it. Too bad for them. But physics is a wonderful way of rewarding morally good behavior. And the people who were forced to do this calculation because the experimentalists needed the answer. So that, by the way, so what it looks like. So sort of 100 pages that looks like this. But people in the late 1980s who needed to do this calculation discovered something astonishing, that if you look at the scattering processes for the particular helicities of the gluons. So the gluons have spin 1, and they can have polarizations or helicities of spin 1 in the direction or opposite to the direction of motion. That, for example, for this simple configuration where 2 of the helicities are minus and the rest of them are plus, all of these hundreds of pages of algebra collapse to a single term. Roughly speaking, these brackets are the square root of the dot products of the form momenta of the particles involved. Okay, so this is insane that these like hundreds and hundreds of pages of algebra collapse to a single term. The complexity is completely apparent. You'd think that it's going to be complicated because you think that what it's doing is keeping track of all these space-time processes in this complicated way, but somehow it's also incredibly simple. The final answer is ridiculously simple. So back then, this was not universally recognized as a tip of a giant iceberg. Today, we know it's a tip of a giant iceberg. But one thing that's clear is that that the standard picture that we have for thinking about these things, it has a purpose in life, which is to manifest the rules of space-time and quantum mechanics. But it's doing it at the expense of hiding something else. It's hiding some extraordinary simplicity, structure, something else is going on. And so this now opens up a program to try to understand what is this simplicity, what is this structure. It's whatever it is going to make some other things obvious that are hidden now. Presumably in this other picture, space-time and quantum mechanics are not the stars of the show. And presumably if you understand what this other picture is, then you'll get some beginning of a clue for where space-time and quantum mechanics might actually come from. Okay, so that's the... So if I say this yet another way, part of the purpose of what many of us have been trying to do is come up with not new ways of calculating these amplitudes using tricks and simplifying complicated expressions and so on. That's of course part of the practical part of the adventure. But fundamentally, at least what I care about is I don't care about the amplitudes specifically themselves at all. I don't give a rat's ass about the amplitude for 3 gluons in, 3 gluons out, or 2 in, 4 out. I don't really care about them. What I really care about is what's here on this slide. I don't so much want to know what the amplitudes are. I want to find a question. I want to find a new question to which these amplitudes are the answer. The conventional question to which you're the answer, again, the experimentalist just throws particles in from infinity, measures them out at infinity. They don't follow the particles in to see this hit that and that happened. They just collide them. It's the theorist that comes in from the outside and say, aha, I'm going to explain what happened in this collision by saying that this particle came in first, this hit that, then produced that virtual particle, blah, blah, all these things happen. I sum over all the ways. This is in the mind's eye of the theorist, who sort of fills in this question mark with local and unitary evolution in space-time and Hilbert space in order to say that that's what's going on. That's the question to which the amplitude is the answer. And what we're looking for is something else. We want to find another question. And here the inside is not going to be filled in with particle trajectories moving in space-time or wave functions in Hilbert space. We refuse to talk about those things. These questions should live directly in the space that specifies the data of the scattering process and not have any extra auxiliary stuff in it and somehow directly give us what the amplitudes are. And the fact that the final answer is so astonishingly simple is another clue that such a thing must exist. And it has a purpose in life. It should explain where the simplicity comes from and many other things beside. So if I have to sort of contrast this, so one way of thinking about what we're looking for here is a version of this idea of holography, but not in anti-de Sitter space, which is this sort of tin can where the time on the boundary is the same as the time on the inside, but in something more like flat space to begin with. We'll talk about cosmology at the end. That's the goal. That's the top of the mountain, is to understand these things for cosmology. But to begin with, even thinking about it in a flat space, it's not so much that quantum mechanics is sort of is king or queen and space emerges from it. It seems much more likely that quantum mechanics and space-time will be sort of equally unfundamental and will emerge together from some other principles. And I just want to say, I want to say a few more general comments before going through sort of one example in a little bit of detail, and then we'll close. The general comment that I want to make is that if there are these structures underlying space-time and quantum mechanics, I think it's obvious ahead of time that they have to involve both new physical ideas and new mathematical ideas. Of course, it's obvious that they should involve new physical ideas. It's new ways of thinking about physics. But it's equally obvious they have to involve new mathematical ideas simply because we have such a humongous structure that we've built up over 60 years of path integrals, Lagrangians, all this structure. The final answers for these observables are not these Mickey Mouse functions like sine theta. They're like very complicated, interesting expressions that come out of this sort of sophisticated formalism. If we're going to get all of those same formulas out of something else, then clearly it has to have some beef to it to be able to produce these interesting expressions. So we should be on the lookout for both new physical ideas and new mathematical ideas. And it's very likely also ahead of time, of course, we'll see this in examples, that the mathematical ideas, if they go along with anything we've seen over 400 years of developments in physics, they should be simple and deep, but likely more abstract than the kind of mathematical ideas that we've worked with before. All right, so let me just say a few words about what the physical ideas are and what the mathematical ideas are. What some of the physical ideas are and some of the mathematical ideas are that have been seen over the past decade and a half or so. The main physical idea begins with this dichotomy between what you could think of as on-shell and off-shell particles, or real and virtual particles, as we'll talk about in a second. A real particle is something that has an energy and a momentum. And Einstein tells you that E squared minus P squared is equal to M squared. And we say that this is on the mass shell. The word shell here is because it looks like a hyperbola in energy momentum space. Okay, so the energy is constrained if you like to lie on this hyperbola. E squared minus P squared equals M squared. On the other hand, when we draw sort of pictures like this, Feynman diagrams, particles 1, 2, 3, 4 colliding here, the momentum of this particle in red, this intermediate particle in red, by momentum conservation is a difference of P1 and P2. And in general, if P1 is on shell and P2 is on shell, then this capital P in the middle here will not be on shell. So that's not a real particle. It's a virtual particle. It's not on the mass shell. That's good because in the Feynman rules, we have these 1 over p squared minus m squareds. So if it was on the mass shell, everything would be infinity all the time. So it's very important that they're off the mass shell in order for the expressions to not just be constantly divergent. Okay. That's again associated with the dichotomy between real and virtual particles. Exactly the same thing. Real particles, I'm now saying things more in position space, if you like. Real particles propagate out to infinity. They come in from infinity. They propagate out to infinity. Virtual particles, and there are things that go click, click, click in experimentalist detectors. So they're real in that real sense as well. Virtual particles do not. They propagate over finite distances. That's the sort of Fourier conjugate of the momenta not being exactly on shell. And again, these virtual particles are kind of a fiction. They're a fiction that we introduce as theorists in order to manifest the rules of space-time and quantum mechanics in our calculations. And they're also the origin of all the horrible complexity when you do the calculations. Okay? So the physical idea is stay on shell, don't go off shell, or eliminate virtual particles. Never talk about virtual particles. Learn to do physics in a way that you only ever talk about real particles. Okay. Now, if you do that, you might wonder, how can you possibly know, if you're going to try to do something like this, how can you possibly know whether you're on the right track? After all, we think that virtual particles are amazingly important in all the ways we have of thinking about this physics in simplest things in field theory. So, how can we decide if we're even remotely on the right track if we're trying to get rid of virtual particles? What lets us do it, and this is the main driving force of this entire subject, is the ability to check if you're right or wrong, theoretically. We don't, the dominant way to check if you're right or wrong, the most exciting, the most important way of checking if you're right or wrong is when experimentalists interact with theorists and tell them that their theories are wrong. But the second best thing that you can do is confront your ideas with theoretical data, which means that you're still confronting them against the rules that we know about nature. We're still confronting them against relativity and quantum mechanics, which are, of course, themselves ultimately derived from experiment. It's just that we've codified all these old experimental results into simple to check mathematical properties of observables like amplitudes that let us see whether they're compatible with relativity and quantum mechanics. And the point is that they're very simple checks that you can do on the formulas to see if they're compatible with relativity and quantum mechanics. So for example, when we imagine that we have a virtual particle here in this scattering process that's in 1 and 2 produces something in the middle, goes to 3 and 4. One feature of the presence of that virtual particle is that it can become real. It can become real when the energies and momentum on the outside are tuned such that the momentum in this interior guy actually does go on shell. Okay, if it does go on shell, then the particle isn't virtual anymore; it's real. And the indication of that is that the amplitude blows up; it has a resonance there. Okay, so and again, we think about that as a virtual particle becoming real. So the indication of being compatible with local interactions in space-time are that these amplitudes can have singularities, but the singularities can only occur in places that we can interpret as the production as virtual particles becoming real. That means that the amplitude can only have poles when, for example, p1 plus p2 squared equals m squared. So it can only have single poles that look like 1 over p squared minus m squared. It can't have double poles or triple poles. It can only have single poles like that. It can't have poles that look like 1 over p squared q squared minus r squared t squared. Okay, it can only have these simple poles with this interpretation. Okay, so that's the rules of space-time. And now quantum mechanics also tells us something. It tells us that in the neighborhood of these poles, we have to be able to interpret the amplitude. We strip off this pole, but the residue on the pole has to be interpretable. It's an amplitude of producing this real intermediate particle, and then having the real particle travel some distance and decay. Okay, so this is a sharp statement that in the neighborhood of the pole, the residue on the pole should be given by the product of lower point amplitudes. So if I summarize the rules of space-time and quantum mechanics, and the simplest processes here, these are diagrams that only look like trees. In the very simplest processes, The rules are that locality tells us we only have simple poles when some of the subset of the momenta go on shell. And unitarity tells us in the neighborhood of these poles, the amplitudes have to factorize into the product of, there's the residue on the pole, has to factorize into the product of amplitudes on the left and on the right for producing the intermediate particle that goes from being virtual to being real. So what this means is that if someone went and claimed to sum those 500 pages of algebra for the example that I was showing you before, you can check whether they're right or wrong without doing the whole calculation yourself. You can look, where are the poles? If they have any poles that don't look like this, they've screwed up. You can check on a pole, look at the residue on the pole and see if it factorizes into the product of lower point amplitudes that they've computed for you before. If they don't, they're also wrong. So these are sort of specific mathematical checks that you can do on the amplitude to check if they're compatible with the principles of space-time and quantum mechanics. But once you realize this, you can turn it on its head, and this gives you a sort of a concrete strategy for this program we've been vaguely talking about. What we'd like to do is to find a different question, blah, 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 to which the amplitude is the answer. But now we can say it more precisely what we're looking for. We want to find a different question. The question be posed directly in the kinematic space. In other words, the only data that goes into the scattering process are just the momenta of the particles, n particles, n4 momenta of the particles. We want to find a question in the space of n momenta to which the amplitude is the answer. And we want to do this without ever referring to particle trajectories or wave function, quantum mechanics, Hilbert spaces, none of that stuff. But how can we know if we're right or wrong? Well, whatever this is, it has to have poles in the correct spot and has to factorize correctly. So we need to find a different question that produces objects with poles in the correct spot and which factorize correctly. This question, this more concrete question, is what we've been now pursuing for 15 years. This is concrete enough that you can get up in the morning and work on it, especially because we have an ocean of theoretical data in the structure of amplitudes, and more recently in cosmology, that gives us a very good guide of the kind of sort of magic to be looking for in the nature of this question mark that produces functions with all these very rigid and special and magical properties. And the emerging picture, it's a very rough picture, but the emerging picture is that in this space of the n momenta of the particles, our canvas, where we're living, there's some fundamentally combinatorial structures, combinatorial mathematical structures, which then uplift to some geometric structures. These are what are loosely called positive geometries, that in turn uplift to some functions, or more precisely, some differential forms that are locked to the geometries, that are functions that are determined by the geometries, functions that have singularities that correspond to faces of the geometries in a way that I'll say a little bit more in a second. And as this process moves forward, ultimately we can connect them to amplitudes and even to observables in cosmology. The words that have been going along with this over the past, in this period, are the story of the amplituhedron, in 2013, isosahedra, that was for gluons, but in very special theories with maximal supersymmetry. The sort of supersymmetry began to be transcended back in 2017 with in a simpler set of theories I'll say a little bit about. The corresponding object called isosahedra. The past sort of 5 years ago, they were developed further. The past couple of years have been many developments in this general area, as well as extensions of these pictures to cosmology. What I find exciting about these ideas collectively is that they describe the real world in some reasonable approximation. They're not literally the real world, but they're not toy models in 2 dimensions that almost nobody gives a rat's ass about. I mean, there are real things about the real world. Not the literal real world, but they describe the real world in some reasonable approximation. And just sitting under our noses, real magic in physics right under our noses, where no one thought anything cool or interesting was happening, there's this enormous sort of subterranean world of amazing connections that have been unearthed and still need to be understood. Okay, Daniel, can you tell me how far over time I've gone? Do I have like maybe 10 minutes?
Uh, yeah, just about, not more. 10 minutes, yeah.
Oh, not more. Okay, fine. All right. Let me then, all right. Okay. Okay. So I want to give you at least one example of what this, one concrete example of what this looks like. So for this, I'm gonna, of course, skip a bunch of slides. But maybe I'll just say that one of the sort of key ideas here is that you can have a geometric space, and these are these positive geometries. Positive geometry is loosely a region P in some space that has boundaries of all codimensions. So, for example, a triangle would be a positive geometry because it's two-dimensional, but it has one-dimensional edges and zero-dimensional vertices. Okay, a circle would not be a positive geometry because it only has like it has a one-dimensional boundary, but no vertices. Okay, so it's a region with boundaries of all codimension, and it's a real geometry. Associated with this real geometry is a certain function, more precisely a form, a differential form, that has singularities on the boundaries of the geometry and nowhere else. More precisely, it has what's known as logarithmic singularities. That means locally, it looks like dx over x, dy over y, dz over z, just the wedge product of a lot of dx over x's. But the only places these singularities occur are on the boundaries of the geometry and nowhere outside, only on the geometry and nowhere else. So these geometries live in the kinematical space. As you'll see, the kind of ideas that determine the geometries are largely combinatorial. But once you figure out what this geometry is, then this sort of form goes along with it, and that's what will give you the physical observable, like and amplitude. So there's some examples. I won't go through these examples in any detail, but again, roughly speaking, the amplitude will be this form. So you come up with some geometric shape. I'm telling you this because I'm now going to show you some geometric shapes. But the amplitude is going to be associated with these geometric shapes. Once you give me the shape, a function kind of goes along with the shape, and the function is sort of built so that the singularities in the function reflect what the faces of this shape look like. And see, this is now, again, giving more of an entry point into trying to understand where poles and factorization come from. Because now you have to look for a kind of geometry that has a particular kind of face. And then when you go to a face, what it looks like on the face isn't something random, but is kind of the direct product of lower things of the same sort that you've encountered before. Okay, so that's... Okay, so I won't tell you anything about the story of the amplituhedron in one line, but I want to give just quickly in 5 minutes now kind of a self-contained vignette of what this looks like, at least one aspect of what this looks like. And so we can do this by focusing on the very, very simplest theory of scalar particles. These are a theory of scalars that have color. So they're like gluons. Gluons have red and anti-blue and so on. They have color and color bar, colors and anticolors. So this is a similar thing, except they don't have any spin. They're just scalar particles. And so if you draw the simplest diagrams for them and you organize the labels on the outside also by the colors that they carry, it's very simple to see that you only get to draw diagrams where the lines don't cross. So the diagrams look planar in this way, the lines don't cross. So for example, for 4 particles, I'd draw these 2 diagrams. For 6 particles, I'd draw this diagram, its cousins, this Mercedes-Benz diagram, its cousins. There's 14 diagrams in total. Now, one thing that you can see in these pictures is that the poles of the amplitudes occur when like P1 plus P2 becomes on shell, or P2 plus P3 becomes on shell. Or down here, it's when P1 plus P2 becomes on shell, and P1 plus P2 plus P3 becomes on shell, and so on. It's very nice to keep track of all these possible momenta in the following picture. Since the momenta add up to 0, if I draw them end to end, they form a closed polygon. See, so P1 plus P2 plus P3, so up to plus Pn. Since they add up to 0, the picture of the momenta form a closed polygon. And so you can see that all the variables that occur in these propagators are just nothing other than the distance squared between 2 points, I and j here. Okay, so for example, P1 plus P2 plus P3 squared is just this distance between 1 and 4. So the propagators that show up in diagrams are just chords in this sort of momentum polygon. And so, of course, if you imagine you're an experimentalist and you're colliding these particles, the first clue you would see is that the amplitudes for what's going on is that, well, they have poles. You would discover they have poles. You would announce at a conference that they have poles. If you're an experimentalist who's secretly a theorist, you know poles are important, so you're going to do very careful measurements in the neighborhood of the pole. You're going to see the amplitudes factorized into pieces. And theorists in the audience will interpret that as the clue for what's going on. Feynman will say, aha, this means it's coming from Feynman diagrams that I just named after me. A mathematician like Pierre Deligne would say, no, I've seen that before. As I don't know what Feynman's talking about, but this is the first property of the moduli space of endpoints on the boundary of a disk. If you don't know what that means, it doesn't matter. But that's also a deep and simple structure that has this sort of factorization built into it. And that gives rise to the picture of the string worldsheet, ultimately. While Feynman's picture, of course, is the particles in space-time interpretation of what these amplitudes are about. What I'm trying to say is that if this phenomenon of factorization is what you notice, then you're led naturally to these two pictures of particle amplitudes we've had for 50 years, particles in space-time or the string worldsheet. But the hero of the last 3 minutes of my talk here is a lazy and smart experimentalist who doesn't actually care to do any detailed measurements, but just notices that there's an interesting pattern that if you ask, when do these amplitudes blow up? So let's say they like blow up when P1 plus P2 squared goes to M squared for the case of for particle scattering. But then they discover there's no other way to make it blow up after you do that. You can't make it blow up twice. It can only blow up once. But you can also make it blow up when, let's say, P2 plus P3 squared goes to M squared. But you can't have both of them at the same time. Similarly, if you have 5 particles, you notice there's a pattern to how they blow up. They can blow up when P1 plus P2 squared goes to M squared, and also afterwards when P1 plus P2 plus P3 squared goes to M squared, but not in various other patterns. Okay, so now we can see this sort of graphically very, very easily. We can see that the poles correspond to chords of this momentum polygon, and if they're crossing chords, that's forbidden. We don't see them, but we do see. We are allowed to have chords that don't cross each other. So this is an allowed pattern of poles. This is a forbidden pattern of poles if I look at 5 points. And again, these are secretly encoding locality and unitarity. Okay, so crossing chords are forbidden, non-crossing chords are allowed. If I put a maximal collection of non-crossing chords, that gives me a sort of a triangulation of this polygon, and that corresponds to a particular Feynman diagram. This corresponds to a particular set of poles that occur in the Feynman diagrams. The reason this is not allowed is that there's simply no space-time picture that has that. There's no space-time picture that has that you can draw that would have crossing chords. So locality is a statement that the chords can only come together in a way where they don't cross each other. And what is unitarity? Unitarity is that in the neighborhood, when one of these x's goes to 0, the amplitude develops a pole, but on the pole, the residue factorizes just as if you're cutting this polygon along this chord. Okay, so factorizes the product of this guy on the left and on the right. Okay, and what this experimentalist who notices this interesting thing about the way the poles come together will notice is that the pattern in which these poles come together actually can be captured by a shape. So, for instance, if I start with the 5-point case, if I just say, look, I can have no poles at all. I'm going to represent that as the interior of a shape. I can have a single pole that I'll represent as an edge of a shape. So this is this single pole, there's that blue guy. This single pole is that blue guy. And then there's a vertex where these two edges meet that corresponds to having the two poles come together. Then it's already slightly non-trivial in this example that you can actually glue all of these things together and they fit into a shape. They fit into a closed shape. In other words, it's non-trivial that I can find a shape where I can decorate every edge and vertex with a partial or full triangulation in terms of things that don't cross each other. Okay, I'll skip this. It's already much more non-trivial for the case of 6-point scattering. For 6-point scattering, the picture looks like this. There's a three-dimensional object. I won't go through it in detail, but you'll see that every single vertex, edge, and face is decorated either with one chord, two chords, or three chords that are non-crossing each other. And this is sort of highly non-obvious that the pattern of how all the poles can come together is actually captured autonomously by this interesting shape. So this object was discovered in the 1960s. It's called the icosahedron. And so this fact is not in all the textbooks. The fact that the amplitudes factorize on the poles is in all the textbooks. This fact is not in all the textbooks, but this fact actually knows about the old fact. This fact knows about factorization. And that's because if you look at this interesting three-dimensional shape, you'll notice that it has 6 faces that look like pentagons, 3 faces that look like squares, and those faces that look like pentagons. So here's a pentagonal face. It corresponds to this kind of picture with one chord there. And remember, you're supposed to factorize on this sort of pentagon on the left and the triangle on the right. And remember, what is the shape associated with the 5-point? It was the pentagon. And the shape associated with the 3-point is just a point, because the triangle doesn't have any chords inside it at all. So this pentagon is actually secretly this factorization into 5-point times 3-point. Similarly, this square here corresponds to this long diagonal, and that's a factorization into a 4-point times a 4-point. And remember, a 4-point was an interval. I didn't say it explicitly before, but the 4-point case just looks like an interval. So 2 intervals multiplied together will give you a square. So this shape knows about factorization as well as about the sort of remarkable fact that that all of the pattern in which the poles come together are captured by a shape, by this polytope. So that's a clue. This is the beginning of the clue that all of these space-time processes actually are associated with the shape. This abstract shape has nothing to do with space-time, nothing to do with particle trajectories, but there's some sort of abstract, essentially combinatorial shape that's gluing everything together from some different set of underlying starting points. And we can try to understand how to make this obvious. Anyway, I'm really done, so I don't have time to tell you all the work that's been done over the past sort of 5 years that makes this obvious. But the point is that there are questions that you ask directly in the kinematic space. So again, our canvas, our space is just the space of all the momenta. And these momenta we can sort of trade for these distances that I talked about, the distances between ij, these xij. So that's our space, just the space of these xij's. And it seems like there's nothing you can do in that space until you just start drawing a grid where you record what all the where you record what all the ij's are, and somewhat miraculously these simple structures start emerging from the space, such that these kind of remarkable shapes emerge out of very simple and natural questions that are directly posed in this kinematic space, with then a reason why the properties of locality and unitarity emerge. Locality and unitarity emerge from ultimately positivity properties that are encoded in these objects in the kinematic space. All right, I think that's all I'm going to have time to talk about here. I want to say a little bit more about cosmology, but I think I won't say much about it here. I'll just end by saying that over the past 15 years, we've seen sort of concrete examples where the rules of locality and unitarity of space and space-time quantum mechanics do emerge from some more primitive mathematical rubric. And the common themes have been these notions of combinatorics, positivity, topology, that breathe sort of physics life into what seems like very barren kinematic space landscape. The past couple of years have seen an extension of these ideas much closer to the real world. That there's hidden properties and some unity of many theories, mostly of colored particles. These toy models of colored scalars, as well as real-world pions, real-world gluons, and interesting properties of them, hidden connections between them, and I think there's a lot more to be uncovered. It's also been very exciting that that very similar developments have been taking place in cosmology, more or less starting in 2017, 2018, kind of in parallel. There's a number of different ideas that are also starting to understand how observables in cosmology would turn out to be strongly connected to amplitudes. And in fact, the amplitudes are contained inside the observables in cosmology. So in a very precise sense, the cosmological questions are definitely the deepest ones. The cosmological questions are the most general ones, definitely the most interesting ones. They're still much less understood than the corresponding questions about amplitudes, but we're starting to see connections, more concrete connections between these magical properties in amplitudes and in cosmology. And I'll just sort of give one example that of something that just came up back in December. Of a way to begin with this picture of the icosahedron and kind of just geometrically shave off the edges and the faces in some simple and very canonical way to produce another object. I'm not telling you anything about how these things are related, other than that visually you can sort of say that you took this thing and you shaved something to produce this one. But the sort of pattern of objects that show up here ends up being not computing an amplitude, but computing every sort of possible term that enters in the computation of the wave function, what's called the wave function of the universe in cosmology, at least for a very simple class of toy models. So again, it's been long appreciated that there's a deep connection between amplitudes and cosmology, but the sort of very direct way in which you can go from one object and get to the other is very striking, not understood, very little understood at this point, but one of many things I hope we understand more. And to just end, sort of our canvas has been just this kinematic space, just the momenta of the particles, or even the spatial momenta in cosmology. There's no time, no locality, no metric, apparently almost nothing that's left in this space. And that's why the only structures that we can play with in the end are essentially combinatorial, very primitive mathematical ideas. And that's why, just to stop here, that's why we've been seeing this strong connection between three fields, cosmology and particle physics. They go back and forth. Obviously, they're both about physics. They go back and forth. Amplitudes are contained inside cosmological observables. We know more about amplitudes, so it's going to tell us more about the cosmological observable. So that connection is the cosmology physics connection is old. But they both now connect with these interesting structures in mathematics. And they're primitive structures. They're not fancy schmancy, Calabi-Yaos, blah, you know. They're very, very simple, primitive, deep things in mathematics. And it's inevitable. There's no other way it could be. If this picture has any element of truth to it, it's inevitable that this kind of interaction has to take place for the reason I said at the end, because the sort of space we're living in has almost nothing in it. It's just a bunch of momenta. It's just this sort of these boundaries where the observations take place. And so we have to find some sort of simple and deep structures in these spaces that connect the three fields together. And that's why I think, you know, there's been developments on all three fronts that have brought us to this point. And hopefully we'll discover, amongst other things, many other interesting, fascinating things that will be happening in this this collaboration. But along this particular front, I hope we'll have something very exciting and concrete and new to say by the time we're done in 5 years. Thank you very much.